In this video, we look at the three types of devices we have studied so far, namely resistor, inductor, and capacitors. And we look at the voltage relationship in the frequency domain now, namely the phasor domain. Let's review the voltage-current relationship in time domain first. For resistor, we know V equals to Ri, and for inductor, V equals to L di dt, and for capacitor, we know I equal to C dV dt. For example, let's look at this simple circuit. I have a capacitor here. The voltage is V of t, and the current is I of t. The source, the voltage source is AC. Is AC is in the format of sinusoid, either sine omega t plus phi or cosine omega t plus phi. If other formats of AC, the concept of a phasor does not apply. The reason we want to study the sinusoid AC format alone, because sinusoid is a very, very popular format of AC applied in the household, in industrials. Therefore, because of omega t, omega that's angular frequency, phasor domain also referred as frequency domain. We can see that in frequency domain, the derivative become product. There's no derivative at all here. The format of the voltage current relationship is much simpler instead of derivative. Now let's see how the time domain derivative becomes product in frequency domain. Let's review the phasor again. So time domain Vm cosine omega t plus phi. Phasor is Vm and angle phi. We use notation big V. Big V here denote the phasor. And remember, this is a polar form. We can write in exponential form. Vm e to the power j of phi. Now let's look at this sinusoid sine omega t. So the phasor is Vm phi minus 90 degrees. So writing in the exponential form is Vm e to the power j phi minus 90 degrees. So now we break this power up. That equals to e to the power j phi and e to the power minus j 90 degree. And e to the power minus j 90 degree, that equals to minus j. So therefore, the term left out is Vm e to the power j phi. What is that? That's the phasor for Vm cosine omega t plus phi. So that equals to minus j of big V. So I refer this equation as. So now let's look at derivative in time domain. Suppose V of t equals to Vm cosine omega t plus phi. And then we take a derivative, become Vm omega. That's a chain rule. And minus sine omega t plus phi in bracket. Take this minus sign here as omega Vm sine omega t. From the phasor, that equals Vm phi minus 90 degree. And this equals to minus j of V. V is the phasor for V of t. That's the equation we just talked about. And this minus sign cancel out each other. That equals j omega V. Let's look at the capacitor. So I equals to C dV dt. So I equals to C dV dt. So then what is I? The phasor of I, that will be C j omega V. So that equals to, organize a little bit, j omega c of V. So this is a phasor. This is a phasor of I. This is phasor of V. And this is in phasor domain. The relationship of the current and voltage becomes proportional to each other by a complex scalar, complex constant, j omega c. The time domain I equal to c dv dt. This is v, small v, that's time domain. and this is the current I. So the sign on the capacitor, that will be plus and minus, and the current of I is flow into the positive sign of voltage on the capacitor. The passive sign convention is followed. In the complex domain, we follow the same concept of passive sign convention. You can see this is a capitalized bolded letter that's phasor, and this is become phasor. Capitalized bolded I equals to J omega C and multiplied by V. So this is exactly we just derived I equals to J omega C V. They're in phasor domain. If we look at the rectangular graph, this is a real part, this is the imaginary part. Suppose this is a phasor of V, there's a phi here, angle, and I can see I leads V by 90 degree. 90 degree come from this scalar of J, because J is 90 degree. This is I, so I is leading the voltage by 90 degree. Or we can say V is lagging the current by 90 degree. In the complex domain, real part, imaginary part, so this is a J. The magnitude is 1. So what's the angle of J? That's this much. That will be 90 degree. So therefore, there's a J here, and omega that's real, and C is a real number. They're all positive. Therefore, I, the current, will lead V by 90 degree. If we understand the current voltage relationship of capacitor, the inductor just swap the current and the voltage. Here we look at the V time domain voltage equals to L di dt. So phasor domain V equals to J omega L multiplied by I. I is the current in phasor domain. In this case, V voltage is leading the current by 90 degree. Of course, for resistor, in time domain, V equals to I multiplied by R. In phasor domain, of course, V is still equals to I multiplied by R, but this is in phasor domain now. You can see here, if this is a V, this is I, they share the same phase, same angle. So if I have a circuit, instead of a capacitor, I have now a resistor now. V of t proportional to I of t by R. So V of t equals to R, I of t. And this is a scalar. This is a scalar positive. So of course, in phasor domain, that will be phasor V equals to R multiplied by I.